And you can take it away. Standing here is nice. Projector right here. Go ahead. All right, hey everybody. Thanks for coming to the first FOCI, now rebranded GenAI users group meeting. Last semester we did the LLM users group meeting, but being more inclusive this time around. Our speaker today is Bill Huang. He's a fifth-year applied math PhD student here working with Rongji Lai, and he had the opportunity over the summer to go intern with a small group in Microsoft and work with Jaron Lanier, if you know who he is, and if you don't know who he is, you should. And he can talk about it a lot better than I can, so I'll let him take it away.
Hello. So thank you for showing up. Today I'm going to talk about how you can use large language models to so-called speak the world into existence, which is extremely ambitious. And this is kind of, you can think of it as like a North Star goal, so to speak. This is like the holy grail. You know, you kind of, as Aaron has mentioned, so let me show you. Okay. So let me first introduce you to kind of the team that worked on this project. So like Aaron mentioned, so this was my summer project last summer. And it was at Microsoft, and they have this kind of research branch that's kind of experimenting with like different aspects and kind of exciting applications that one can use with large language models. And in particular, I was working with two other interns. So top left, that's me. And two other interns, Fernanda and Kathy. They're both from MIT. One's from the Brain and Cognitive Science Lab, the other from the Media Lab. We had two mentors, Andy and Judith. They are both principal and senior researchers at Microsoft. And then finally, our manager, Jaron Lanier. I don't think a lot of people know him these days, but he was once yeah, I think he's very popular among certain subgroups of subcultures and subgroups of people. Probably most famous for inventing the word VR, virtual reality, and popularizing it by creating the first commercially viable company to create VR products. He is kind of old now, but he's still active. He's still very sharp, which is extremely impressive to me. But anyway, that was the team. And this talk, the general structure is gonna be the following. So it will kind of have two parts. The first part, I will kind of introduce you to this kind of overarching framework that we have kind of developed during the summer. We call it LLMR, Large Language Model for Mixed Reality. Kind of the TLDR one sentence summary of this model is that it's kind of a framework that can allow you to do real-time generation and modification of virtual scenes, objects, worlds, what have you, using large language models. And this is done in Unity. For those of you who are not familiar with it, Unity was developed as kind of a game engine. So it's like a platform you can like write and implement video games. I don't think anyone will dispute this. Probably the two most kind of popular and famous frameworks out there is Unity and Unreal. Unity, I think, have more people. There are more people who knows how to use Unity because of its simplicity, and that's why we chose it. So the first part of the talk, I will kind of introduce this whole system that can do many different things. A lot of it I will show you in just a minute. I will talk about kind of briefly the kind of how the framework functions as kind of an orchestration of different language models. And then I will move on to the second part, which is you can think of it as a particular component of this framework that we have developed. In particular, we're using this framework to do animation creation in real time. And that's something that really excited me because me personally, I really like video games. I think any kind of application between AI and video games is extremely exciting. So yeah, couple more things I'll mention. So one thing I'll mention is like 2 weeks ago we got the notification this was accepted to Kai 24. Pretty happy about that. And I will this talk will be kind of light on the technical details, but you're more than welcome to ask me about anything down to the tiniest detail. I will more kind of focus on just showing you like a lot of videos of what it can do and kind of applications that we kind of have dreamed that maybe this can do. Yeah. So without further ado, let's get into it. So let me start with kind of the minimal example of how you can use our framework. Okay, so on the screen, which I hope the definition is good enough, but essentially this is like this is kind of a screenshot on the Unity, the game engine that I have mentioned. And what it is that so these kind of boxes are we put into the code we wrote into the game engine. So you can think of what we are doing is we're kind of embedding a language model inside a Unity engine, which supports all sorts of stuff like object creation, physics, like lighting, like just all sorts of these. Many people have worked on it over the years, and we're kind of trying to push the large language model to see how much it can leverage and harness the ability that's embedded in the Unity engine to create and modify these kind of virtual scenes. So this first example, what I will show you is you can use our framework for just simple object creation. That's certainly possible. So how it works is that there's this text box on the bottom. So yes. The main code is not open source yet. We're working on it. Their legal team, I don't know. But part of it, for the second part of the talk is, I can put those links up. I can certainly give you the link to the paper.
I just want to
Okay. What was I? Yes. So how you will interact with our framework is that you will basically just type there in the text box here that what you want to do in this existing scene. There's nothing here, so maybe you can just create something. So here, let me just show you. Hopefully you can see what the text is. So here I will just do a really simple thing. What I will about to type eventually is I will ask the framework to create a cube, and the cube should be rotating. And while it's rotating, it should change its color every second. So very simple. You can program this yourself with some effort. But you can also ask GPT to do it. So then I send the request to the framework that we have. The framework does some processing, including like coding and doing inspection. The details I will go into just in a little bit. In about like 20 seconds, it will finish everything, and then you will execute that code, and then the result will be shown on the screen. There you go. Rotating cube, changing color. So this is a very minimal example. So let's see how far we can push this. So I'm about to show you a lot of videos. You will have a lot of questions. I will appreciate it if let's wait till all the videos, the demos are shown. I'll take questions then. First thing I'll show you is you can do object creation that's a little bit more involved. So in this particular demo, I will show you kind of the creation of a very simple toy car. It should have like a semi-believable appearance, but also you can kind of drive around with it. So this is a sped up version of that video. So here we just prompted GPT to create a car, then we prompted to color the car, we prompted to make the car like interactable and drivable, and then we can put the car into like a terrain, and then we can actually drive it in the terrain to see that it is actually functional. The terrain was not generated. This is like we put it there. But the car, everything, all the steps into creating this like semi-functional car is completely generated by the language model. Here's another example. Here, I'll call it a scene creation. So what we've done is we've created a kind of a I would say a moderately complex scene. In this case, it's a kitchen. So I've cut out the part where it's actually like I gradually prompt the language model to do this because that took a while. This is the finished product. I would just highlight a few things. So to me, what's really interesting here is that so everything here is created by GPT, including all the objects, their appearances, their relative sizes, positioning, and colors. So you can see that there's like this. That's kind of an oven with like the furnace stovetops on top. There's a fridge over there. There's a table with salt and pepper shakers. You can see that all of these things they're kind of placed in actually kind of a rational, like semi-sensible order, and their scales are believable. So GPT or language model certainly has some like kind of physical intuition as to like how these things should look, where they should be placed right next to each other. You can take this further. So let me show you kind of a different set of examples. Here you instead of kind of creating objects from like the vacuum, what we have is kind of an existing scene. So this scene is kind of a bathroom scene, which I grabbed from, I think, Sketchfab, which is like an online repository for 3D models. So someone else made this scene, and it looks pretty and stuff, but nothing in this scene is kind of interactable. So for example, the lights, they're all fake. They're just visuals. The faucet here is also fake. You cannot turn it on, obviously. But one thing I've tried to make GPT do is, okay, I say, okay, can you make the water flow out of the faucet when I click on it? And I also give GPT a little hint. You can do it without, I said, use particle effects. You can do it without. It's less reliable, but it can still do it. Here I use the hint, and GPT goes processing in the backend. I'm just focusing my camera on the actual faucet. Speed up to when it's done. Yeah, so once it's done, you can click on the faucet, and then you can see that it has produced some kind of particle effect on the faucet. And the other thing is that if you, let me go back a little bit. Well, I guess you can't actually see it without the other thing. So I guess it's blocked by this like box here. But one thing is that the water is coming out of the faucet is not actually colliding with anything in the environment. So for example, there's the sink that's like below it, right? So in physical reality, the water coming out of it will like collide with the sink, and the sink will collect the water, right? So you can further prompt GPT to like make alterations such like these. GPT will try in this case. I may add, maybe not super well, but you can see that it is colliding with something. So at least it's trying. Let me show you another example. This one, the idea is that I want to make it so that I can kind of interact with the environment in different ways. So for example, here my idea is I want to ask GPT, okay, can you make it so that you turn my mouse, the clicker I have in the virtual environment, into kind of a texture stamp? So the idea is I ask it so that if I right click on a certain object, I will kind of capture the texture on that object. And if I left click, I will transfer the saved texture of the object I right clicked onto the object I left clicked. So it's kind of a, I would say it's kind of a moderately complicated task that I've asked GPT to do. I'll just skip over to where it finishes. Okay, so here it's finished. So then I right click on the wall, I left click on the bathtub, there you go. And I right click on the painting on the wall. And I left click on the bathtub, there you go. One last thing, I click on the plant. And I click on the bathtub. So there it is. I'll show you a few more in this direction, but I will, one thing I'll emphasize is that these, we have more of a application in mind. I think the previous few were more just maybe playing around. These, I want to invite you to think of as the potential application is maybe accessibility. So maybe if there's someone using these kind of, apps or like these kind of they're having this virtual experience, right, in the world, and they wanna many times, right, everyone has their personalized kind of preferences and kind of accessibility needs that it's very hard to cover, like have a catch-all kind of programming design in the original software. And our idea is, well, maybe the prompt-based technology can kind of cover much more bases, much more kind of naturally. So one idea is, for example, here. This is a scene I grabbed from, I believe, AI to Thor or Author. It's from the Allen Institute. It's originally used for training like robots for like reinforcement learning. But here we're just using it for our purpose. The idea for this video is that, okay, suppose, so I wrote the prompts here. So suppose you're someone who's red-green colorblind, like me. And you look at this room and you know, most of the colors are fine, but if I may be honest, I don't know what this color is. I think it is yellow, but I'm not sure about that. It could be green, could be yellow, could be orange to me. So just all mushed up. So I could prompt GPT to say, okay, can you make the room more accessible to me? I didn't tell it to how to do this, but I just given my demands. And GPT goes coding after a couple of seconds. There it is. So it knows how to, I think it's, yeah, so it definitely writes some code in the background to go through all the objects and then change their color scheme. And the cool thing is it's able to understand like what kind of colors are more friendly to a red-green colorblind person. I'll give you a few more examples. So maybe you have terrible eyesight, also like me. So you, maybe you wanna have some kind of like customized magnification tool. So in this case, the idea is, okay, can you, I'm asking the framework, okay, can you make it so that my mouse becomes a magnifier and wherever I click, you're gonna, the screen, the camera is gonna zoom in to the place I click. Moderately complicated, I would say. I don't know how to do this. If you ask me, I probably look up some tutorials. But turns out that the language models do. So let me maybe skip a little bit to where it's finished. Okay, there you go. So it's finished now. And then I'm testing it. So yeah, so somehow, some way, is able to figure out kind of the perspective shifts and like this zooming and zooming out kind of dynamics. One last thing, also kind of goofy. So suppose we wanna, so we wanna take this room, we're having a virtual experience, and we wanna put this room in kind of a party mode, all right? So I'm asking the framework, okay, can you kind of put this room into the party mode and do so through kind of manipulating the lights, you know, do a little light show, something like that. And GPT will go coding, and I will show you what it looks like. So there you go. I don't know if that's my idea of a party room, but GPT certainly thinks so.
Well, it's inaccessible.
Here's a kind of another kind of category of applications we're kind of maybe dreaming about. Is what we call remote assist. The idea is that you have a lot of these frontline workers in like hospitals or like firefighters, and a lot of times they need a lot of training to be able to do the things that they do kind of effectively. And virtual reality, VR as a whole has been like very useful in this respect in terms of like training them to do certain tasks. But you know, producing these kind of training guides and like videos experiences are very kind of like manual and like very difficult. It takes a lot of resources. So we thought, okay, can we kind of generate these guides automatically? And this is one such example. Here, the coffee machine and the hand are not generated, but the movement on the hands, as well as kind of the posture or like the gesture the hand is currently are all determined by GPT. So we're just prompting GPT to do, okay, can you make the hand, can you generate a guide that tells this person how to make a coffee, and then it comes up with the steps, and then it comes up with the movement of the hands as well as the cups. Two more. Since we said this model is in virtual reality or mixed reality, we also have a few VR applications. One such is, if you know VR, there's this app called, I think just Magic Paintbrush or Magic Brush, that allows you basically just to draw things and like just kind of like express yourself with like the paintbrush that's like in the that's on your controller. So we were able to kind of create a very simple version of this app just by prompting, basically. And you can make this, the idea is that, well, you can make this very customized, and what used to be kind of like a very complicated programming like process making these VR apps, you can maybe now make them much more easily. I think there's the last one I will show, which is kind of a funky example again. The idea here is that you can also do some kind of gesture recognition with it. So the hand gesture is recorded by some kind of like video device. However, the recognition of this particular gesture, that's determined by GPT, and also linking the recognition of the gesture to the cat being startled. That's all done by just prompt-based technology. Okay, I think that's all the videos I have. I'm gonna highlight a few things, which I've given this demonstration to a good number of people now, and every time people kind of have the same amount of questions, which I will kind of cover just as a preventative measure. So the first thing is one thing that people ask us a lot is whether we're using any kind of vision model, because a lot of these tasks would appear that you need some kind of model to do kind of object detection or like kind of segmentation or whatever have you. In fact, not. So everything I've shown you before, I said except the AR demo, but I didn't actually show you the AR demo. So everything before is actually, all the videos I show you is actually only done through just the language models. Everything that I showed you before has no other modalities involved other than text. All that the language model has to do is to code in Unity, and it can make all of those happen. So the second thing I really emphasize is we did no fine-tuning on GPT-4 as it was back in the summer when we built this framework. So in other words, we prompt engineered the heck out of it. But I'm kind of using prompt engineering in a liberal way here. I will show you just in a little bit what I mean. But essentially, what we are building here, I think a large part of our technical contribution is that we actually have kind of a multi-agent orchestration going on that's eventually eventually contributed to the success of like being able to do all those demos. So if you just use the standard off-the-shelf GPT, you will not be able to do most of those. So I will discuss in just a little bit how we're able to actually do this. Two other things I want to highlight is I think it's also very cool that we're kind of exploring generation of kind of these virtual worlds that's beyond the visual aspect of it. So, you know, I think that by now we can generate images extremely well. I think we're also beginning to generate videos very well. But a lot of these efforts are still very focused on just the visual aspect, which by itself is already very hard. But I think the more ambitious goal here is to kind of dive into different aspects of what constitutes kind of a meaningful virtual world, such as it is. So it has its internal degrees of logic, internal degrees of freedom, its own like inner logic, stuff like that. Last thing I want to emphasize is that the framework is built not just as kind of a development tool. So large language models a lot of times are just used in development time, meaning that, say, I'm a programmer, I don't know how to write some piece of code, I use the large language model to help me with that piece of code. Here we're kind of, we want to move beyond that in the sense that we want to make we want to give power to the users in the sense that we want the user to use this framework. And this user doesn't need to know how to do any of the programming stuff. They can just use this in real time. Think about accessibility. If they have needs, they just ask the framework on the spot, and the framework will do the bidding. So that's kind of a perspective change in this sense. Okay. So now I'll move on to kind of delve into the details of how exactly this all works. So what exactly did we do to make this happen? So to explain this, I will also kind of have a little example to go with it. Again, a very simple example. So to start with, I think the most general setup that we have is that you have some kind of current scene that's some kind of existing virtual world object or what have you. And as the user, you're in this scene and you want to kind of do something with it. So let's say that, on the right, we have this virtual scene, which looks like a children's room with there's various toys in the scene. In particular, you have this teddy bear that's in the corner. And let's say that, maybe you're a kid using this virtual software and you're like, okay, I want to make this teddy bear twice as big. Okay. So very simple request. Let's see what our framework does in order to be able to carry out this request. So the first thing is that has to be some level of understanding that's happening. So because if you think about this request, right? So it says make the bear twice as big. In some sense, our framework must be able to kind of look at the existing scene and then determine what the user is referring to when they're talking about the bear, right? So how that works is the following. So when we see this virtual scene, because I mentioned there's no vision models, there has to be some kind of textual representation of this scene that's being fed to the language model. And that's something that looks like the following. So this text, it's kind of readable. So what it is like a JSON file of the hierarchy of objects and their relations in the scene. And here, this is parsed by just like a manually written script going through the Unity backend. So as you can see that, it gives the scene, the name of the scene and the various objects, their positions, relative scales, orientations, etc. And what our framework does is that there's this first, yes.
It generates that.
This one?
Yeah.
This one is automatically parsed. So there's a fixed script that does this. There's no AI involved in this step. So what our framework does is that you get this text from that virtual scene. And what you first do is to feed this text into what we call the scene analyzer, which is by itself is a language model, but properly prompted so that it knows what its role is and all that. What it will eventually do is that it will take this whole string of text representing the entire scene and then only outputting the part that's relevant to the user's request. And in this case, that's the bear. So the scene analyzer is gonna take this as its output. So the relevant object bear, that's the output. And you will kind of pass it down to another GPT that I will soon cover. There's the skill library here, which is not actually used in this particular example. I will cover more of it later, but you can think of it as like kind of a collection of plugins for the language models. It's like kind of a specialized library of specialized skills. So this is a simple task, so we don't need this. So the scene analyzer has looked through the scene and determined that the relevant object is the bear. So what it then does is to pass this information down to what we call the builder, which is another language model. And the role of this language model is that it just writes code. It's going to write the code that does what we want it to do, which is to make the bear twice as big. And in this case, it's the code that it writes is something like I'm showing on the right. But before we kind of go ahead and execute this code, what we found is that a lot of the times, even as good as of a coder as GPT-4 is, it makes a lot of mistakes because kind of the space of the requests that user can ask for is extremely big. And programming in like a game engine is no easy feat. So it'll make a lot of mistakes. And what we found that is that there are a lot of, for example, repeating mistakes that we will still make, even if we caution it against them. So what we have finally arrived on is this design choice of introducing another GPT we call the inspector, which checks the builder's code before it's being executed. So when the builder has come up with a draft of the code that he wants to execute, this draft is first passed to another GPT called the inspector, and the inspector will look through this code and see if there's any like potential errors. And in this case, it has determined that there is, and then it will kind of refer back the suggestions to improve this code back to the builder, and the builder will try again. And this iterative process will continue until the inspector is happy. So after 2 times, the inspector is happy, and then the code is passed down to a compiler, executed, and then it will do what it's supposed to do. So that's the general framework. Again, a lot more details in each of these components. I'm happy to answer if you want to ask about them. One thing I would highlight is that we have done some quantitative experiments on all of this. So one graph I would show is that basically you can compare this kind of multi-agent or multi-module orchestration to just using a single GPT. And what we found is that, and we do this in a lot of different scenarios across different requests and prompts. And we found that is that if you use all the modules that we have previously mentioned, you can achieve up to like 3 or 4 times less of an error rate when carrying out the user's request. An error is defined as, so the user gives a prompt, and then the error is when the code is being generated, the code either contains runtime or compilation errors. Yes, yeah, that's a very good point. So that does not mean that you did do what the user wanted you to do, like completely, but that is very subjective. So we opt for like a more kind of objective, a conservative way of measuring this. Yeah, right. So, but towards that point, if it has a runtime or compilation error, then we can always say that it has failed. So that's why we use this metric. SA is the scene analyzer. SL is the skill library. I is the inspector.
Skill library is special functions that.
Yeah, that's some of it. It also has, like, for example, when I show you like the whole VR kind of set of demos, there's some like additional kind of like APIs with the VR libraries, and it may not like know about those or like call those very consistently. So we provide them in this external skill library.
Is the inspector or builder module interaction, is that like an adversarial or and also the question is, how does, if one of them makes a mistake, how does the other one sort of know that's a mistake?
Yeah, it's a really great question. So let me answer one by one. So so the first question is, the inspector actually is the underlying model is all just GPT. They're all the same. What makes them different, being one is inspector, one is builder, is that they have kind of a preamble paragraph that I use as part of the prompt. And for the builder, the preamble, I say, okay, you're kind of a coder that's supposed to write the code that executes the user's demand, whatever that is. And for the inspector, the preamble I wrote is something like, you're a careful inspector who will look over a piece of code and determine it has any errors and stuff. So you kind of give them different personalities, like, so to speak, by doing this. To your second question, this is a very good question. Which is basically, if the builder didn't know that he made a mistake, why would the inspector know, right? Because you're the same model, you're all GPTs, right? I think there are a couple ways that I can answer this. Intuition wise, I think one is that, which this one, people have argued with me with it, but I think by and large it's true. I don't know what your intuition is, which is it's easier to check a snippet of code rather than to write it. But I think even taking a weaker stance, even if that's not completely true, I think at least checking the code has different kind of error modes, like different ways that it can go wrong compared to actually generating the code. So we're kind of hedging different kind of sources of error together.
It makes sense to me that if you're prompting it differently, cause it to interact.
Yeah, yeah. But it's a very good point that ultimately neither of them know if this is right or not. But yeah, but we did find that this is actually like pretty robust across different scenarios.
After you give it back to them and say, hey, this was your code, but now.
Which part?
Inspector sends it back to the.
So it will send a verdict, which is success or fail, and it will send the suggestion as to how to change the code to pass. Sorry, I guess actually it will send the reason and the suggestion. So yeah.
Just does it.
Yeah, exactly.
When you're telling the other guy, look for these things.
Yeah.
Doesn't much.
Exactly. That happens a lot. Yeah. Yep. Yep. I think there's some kind of, my interpretation partially is that there's some kind of attention deficit in the builder. It's trying to do too many things at once.
There's actually work on it cannot handle a lot of application.
Yeah. Yeah. I mean, when I built this, my intuition was not very mathematical or rigorous, but I think there's definitely like more work to be done in this respect, and perhaps something rigorous you can say about it. Yeah. Okay. Sorry. Yes.
So I'm wondering if you could put the illustration of the room. Right. So, when you're building Unity models, you can either have it so that they actually know that there's a boundary, and the boundary just goes through.
Okay. I think I know what you.
So now,
Yeah.
in asking for the bear to be twice the size, that bear could fit or that couldn't fit, did you play with that at all? Did you make it aware of, like, you want to make the bear 3 times as big as it can't fit?
Yeah. So you can I guess I'll answer it this way. So what will probably happen if you ask exactly that, make the bear 3 times as big, it will make the bear 3 times as big, and it will go out of the room. But if you don't want that behavior, you could maybe say make the bear 3 times as big, but mind like the boundaries so that it's still in the room. I think it will try to check some kind of collision or overlap between the meshes and try to like have a little room between them.
So the other question I had, your bar graphs,
Bar graph.
sort of your experiment.
Yeah.
So this answered a lot of questions. Essentially, the leftmost bar is just raw
GPT.
code generation, right? Yeah, yeah. Raw, just have it generate Unity code, and that's what you get.
Yep,
It's
exactly.
Tons of errors and stuff like that.
Tons of errors, yes.
You've added these both from prompt engineering standpoint and then your textual model. You've added that.
Yep.
LLM.
Exactly. Yes.
Really amazingly badass. Some game companies sort of business. But you can create a video game now to the likeness of the player, and according to his further advantage, so you have really not even a procedural generated game, but a game that the person actually designs and programs as it plays along.
That's the dream.
Wow, just mind blown. We just had a speaker today, just as a side note, now Coxside talk, Method Pisano, he's a PhD in in the computer department, masters in the computer department. He was talking about using the same thing that he did in Builder and Checker, but he was using it to check for adversarial attacks in terms of surpassing the ChatGPT's guardrails and
Okay.
generating
I see.
uranium and getting structures for that.
Mhm.
So he was daisy chaining several large
mhm.
language models, just combining, let's say, ChatGPT and
Yeah.
Llama to do that.
Yeah, yeah, and I think it's definitely a trend to kind of for prompt engineering techniques to move towards more kind of multi-agent interaction frameworks, which I think are, yes.
Doing this builder inspector, saying that this theorem has this iterative.
Yeah. Yeah.
What types of rules were things like, for instance, with the sink and the collision kind of going to like continue correcting for mistakes, or do you have
Yeah. Yeah, yeah,
things collided incorrect?
yeah.
Allowing it to iterate upon itself.
So I would say, so you can tell me if I answer you correctly. So, our intention of the inspector is mostly in terms of kind of mostly in terms of runtime and compilation errors, but also maybe checking some like typical behavioral errors. But for the example that you mentioned, which is kind of more qualitative, like the particles that are bouncing, but they don't look visually quite as good as you would like, right? Those ones we are not really checking for because if you think about that space of problems, they're very subjective, right? So I think if you do want to check for that space of problems, probably some kind of vision model will be nice. Yeah. Yes, yes, indeed. Not the case when we did this, but yes, yes, now it does.
Say, is the water flowing properly in the sink, and then
Yeah, yeah, I would love to try this, honestly, if they give me the keys.
Wondering now, so if what were to actually build a game, say like I found this nice, I'm gonna put stuff in it, make it interactable. Is this like a sustainable way to write code in you? That's a
Yeah.
relatively simple interaction. Is that how people do it in real life?
Yeah, great question. It's certainly not a good design principle from software engineering. There's no modularization or anything like abstraction, anything like that is out of the window.
Does software engineering count design principles?
Well, what I would say is at least we made the framework kind of persistent. Like it is theoretically possible, like you could save all those scripts and they're like persistent in that way and you can iterate on your previous work. That's possible. Whether it's good design to do it like that, yeah, then we don't have anything in that respect yet.
So with your existing framework, if I just put in one prompt and said, make a Gollum video game, would it be better or worse?
I don't know. That's a good question. We have to try it out.
Seeing all this stuff.
Oh, yeah, that's a good question. So we, when we did it, we just used we just coded it ourselves. There's no kind of orchestration package that we leveraged. But I would say we heavily, borrow inspiration from like semantic kernels, and that.
Is that because Unity, there wasn't anything to use to apply to Unity?
Yeah, I think.
It's really kind of.
Yeah, because we're embedding in Unity, I think it's maybe cleaner to just write ourselves.
So,
To that note, I have made like a complete game in Unity before, just a hobbyist. So yeah, I know Unity.
First question that we showed. To clarify, the only pre-built assets that there were the standard Unity ones. No other pre-built assets, all of the objects on the sink and on the stove that were generated, right? The like squares, all of it is ChatGPT, no pre-built assets in the C.
If you talk, so these are existing assets.
This one prior to that. This one.
Oh yeah, all built. Yes, yeah, all built.
But Put that.
That's a great question. There are details to that. In fact, if you just say create a kitchen, it wouldn't be as good. Because it may be very lazy and just give you some bare bones things. Now you can also be very kind of comprehensive and then say, just specify everything in one prompt. So like create a kitchen, it has a fridge should go here, counter should go here, there are toasters on the counter. You can say all of those in one prompt. We also tried that, and that's also much worse, interestingly. So we built, which I didn't cover really here, but we also built a system that allows you to kind of decompose very complicated prompts into sequential steps that each step is like small, contained, and much easier to do. And this kitchen is a result of that. Yeah, it's another language model. Yes. Yeah. Yes. Exactly. You just have the access to the piece that was picked out. You could do it that way, like have the builder having access to everything. There are a couple reasons we design it this way. The first reason is token size limits. Back then there was only 8,000, not a lot, especially given these. But I think also the performance will degrade. I think there's severe kind of, I go back to this term again, attention deficit that the builder has if you just feed this whole thing, as well as all the other guidelines and requests that you needed to do. So. Yeah, I would say to that, I would say certainly if the token size just exceeded, then yeah, that's a problem. But I would say that even like if the token size is fine, then it's actually very good at picking out even scenes, even like extremely complicated, as long as it fits in the token size. So like it's so it's either completely broke or it's like pretty much perfect. So I was pretty surprised actually. Yeah.
The thing that's really fascinating to me about this is, it seems obvious, but it's doing it in this virtual environment, virtual reality. So that it's the language model is manipulating, it's manipulating objects that can have sorts of properties. That initial scene that you just showed, that's a 300. You can immerse in that, where it's not just a stupid picture. You can have it conceivably pose things. It can know that hands have 5 fingers. Right?
Yeah, exactly. And
yeah. It knows it's a hand.
Yep.
One can manipulate that hand.
Yeah. No, for sure. Yeah.
It's so fascinating to me.
Yeah, no, that's definitely one of the kind of the should I say main motifs that we're working along the way, which is like this is to us this is a more kind of sensible or intuitive way of generating, because the language model actually knows what's going on instead of generating an image. Well, you got to dig into the neurons to see what kind of representation and features they learn. But like that's like to me a little bit more unintuitive. In this way, like it actually knows that it's manipulating this part, and it's more interpretable.
So this person on the call who couldn't be with us, Eric Amaris, is bursting. He thinks this is the coolest thing in the world. I don't know if you know Eric is, but he teaches the game courses.
Oh, okay.
Yeah, so he's a god on campus.
Nice.
We did it? Yeah, I haven't seen him. Wow.
Okay, but if you like games, this next thing you're gonna really like. Okay. Okay, so this is the second part of the talk. I'm running out of time. I'm gonna be fast. So this part, like I said before, you can think of it as like a particular functionality of the first like overarching framework. What we'll do eventually is that we'll use the framework we built to generate animations in real time. Let me show you just one, again, the bare bones example of how, like, what kind of things are we talking about here? Okay, so here, the Unity window again. In the window, there's this beautiful whale. Someone else made it. This is a human-made 3D model. It's static currently, so we want to make it move. So the ultimate idea is, well, if we want to speak the world into existence, If the world is all static, that's terribly boring. So we want animation. And this is the part I really worked on during summer. Yeah, so I don't know if you saw, but I typed in the prompt, can you make the whale swing forward? GPT goes processing, and this will last a minute. And then when it's done, it's gonna play the animation on the whale. Should be any second now.
Can you sort of sketch out from a performance standpoint or profiling standpoint, where is it doing most of the thinking? What's taking the most processing time? How's it distributed?
Yes, it's very task dependent. For the previous ones, I would say the coding. For this one, which I will talk about in just the next slide, it's gonna be the part where it's generating the animation, which I will show you in detail how it's done. Yeah, so yeah, I don't know if you saw, but the animation was generated and it's automatically play on the whale. Oh gosh, all right. Well, yeah, so I hope everyone saw that. So now I will just talk about how this is actually done. So I will remind you again that all we're using are language models. No vision model, no like diffusion model on like time series, nothing like that. Language model. So all we can do is to manipulate text, right? So how is this possible, right? Text and motion, like how are those related? Well, it's actually pretty simple. So I'll just give you this example. So on the left, there's this motion of a whale, and the only part that's moving is the tail, right? So because we're using language models, we need a way of kind of representing motion in terms of text, and then kind of process that text with language models and eventually generate the text, right? So the way we do this is actually very straightforward. The motion on the left, I've put the text representation of the motion on the right here. And let me just kind of break it down a little bit. So what it is so there are two rows here. And in each row, the starting part, this part, is what I call the join hierarchy or the joint name. So what it is that this whale has a lot of different joints that it can move, right? So like this. So the part that's moving is kind of the tail joint, right? So the name of the joint is first specified and something like the following. That's just its name in the whole tail kind of bone structure. And the next thing is that if you think about what motion or animation is, well, it's really you just have to specify how the orientation of this particular joint changes with time, right? So at time 0, it's like in this orientation, time 1 is like this, time 2 is like this. And then if you interpolate between, you get a motion, right? So that's what this is. So following the joint name is basically just a bunch of vectors specifying this trajectory of orientation change. And each of those vectors is a 5-tuple. The first entry is just time, and the next 4 is quaternions, determining the orientation. If you know some computer graphics, that's just the best way to represent rotations.
Yes, so you say X, Y, Z, and W for quaternion values. So I'm assuming that is a good way to, I think, like consider the best way to do rotations. But what's the reasoning to have these? Actually, before I even ask that question, which one is your traditional 1, I, J, and K? I'm guessing X, Y, and Z are I, J, and K, and W is the one, or which one, mathematically speaking, would be the 1, I, J, and K? Do you?
Yeah, so IJKL, I guess, the last one.
The last one's
Yeah,
the one?
yeah.
Okay. Yep, so, and then what was the reasoning to do very interesting
Yeah.
stuff, but what was the reasoning to do the quaternion values? Did you see that as the best way to represent
As
it?
alternative to like Euler angles? Is that what you're thinking?
Yeah,
I mean, so it doesn't, you could do Euler angles, but I guess, I'm not a graphics expert, but I think I remember if you do Euler angles, you run into problems like when you interpolate, sometimes it will do this like really awkward thing. Like if you've seen like FIFA games, EA, like sometimes the footballer's head will like, you go like this. And that's what happens if you do like, So this avoids that. Like when you interpolate between quaternions, it's more kind of smooth, like visually.
Yep.
Yeah.
Thank you so much.
Yeah. Gimbal lock, that was the term. You can look it up. Yeah. Yes.
Saying, LLMs are kind of bad at math. How do you force the unit?
Great question. The unit constraint, I guess, were not, well, that one you can, I guess, just normalize. You can do like a post-processing, but being bad at math is definitely a thing. I will talk more about that. Well, actually, I will talk a little bit about it now. So a couple things that really help in that respect. One is that you probably only want to generate the quaternions at keyframes and interpolate between. So you don't want to do a very dense sampling. Like you don't want to like generate a quaternion every like 0.1 second, every frame or even. That would theoretically work, but language models right now probably wouldn't. And the second thing is, if you notice, all the float point numbers only have one significant digits. So that's also something that helps because they're treating it all as text, right? So this way, it's kind of, it'll focus on the more kind of the big picture. Like this should be like about this size instead of getting lost at like the 5th digit, let's say. But yeah, so yes. Yeah. This one, right?
The initial position where you have the angle is also.
Yes, I think I know what you want to ask. Very good question. So we also allow, I didn't write it here for simplicity. We also allow, I think it's called root motion. So the translation on the whole frame is possible. We didn't allow translation on like other joints because those are usually like really unusual, right? Like you can extend this joint like this. That's really unusual as movement. But if you want, that's also possible. For the root motion, we represent it with like square brackets, and it's like a 4 tuple instead of a 5, where the first one is time and the next 3 are XYZ coordinates.
And you did that like manually doing or the
No, it's also model. Yeah, you just have to tell it if you want root motion, do square brackets, and if you for all the other ones, do this. Yeah. Okay. Oh well, okay. Yeah. So lastly, I'll just mention. So yeah. So this is a textual representation of that motion. So ultimately, all we have to do is to output this text and then parse it into motion. We're done. So you just need some kind of language model that can output this text, and that's what we eventually did. So how we did this, I will skip over some details again, but no. So we didn't do fine tuning. Although if you did, I think it would be better. Well, we didn't do it because we didn't have training data. What we rely on instead is just in context learning. The idea is just that, okay, let's say for the whale model, right? Someone already have made some existing animations on the whale model, right? So like swimming, for example. And then we use that as few short demonstrations to the language model. And then we can ask language model to generate new animations on the same 3D model. And to me, it's really interesting to see like how much you can push this, right? If you show it how the whale can swim, how much more can the language model generate? So I will show you that. So this is the demonstration that was used for the whale. It's a human-made animation. It's like swimming, I suppose. I'll show you 6 that's being made with language models. So different kinds, like, so you got tails moving, that one's tail wiggling, this one's tail moving left and right. That one's turning the head. I'm not sure if whale's head can turn that way, but there you go. That one, really interesting to me, it's swimming aggressively, doing this kind of circular motion with the tail. This one kind of goofy, so it's trying to make the whale swimming like flying like a bird. I don't know if it looks like that, but it's like doing this. I'll show you more examples on different models. So this one is like a humanoid character, it's a pig. This is the human-made animation, it's like, I guess, walking. And I made a few more. So here, this one, the first one is very simple. I just say, can you make it walk, but with one leg limping? And there you go. You can make it spinning, jumping, eating. Let me show you a few more. Here, like I think Animal Crossing character. Anyway, some kind of raccoon, and these two are made by human animators, just kind of idle and maybe explaining or talking. I made a few more. So here you can show its disapproval, wagging its tail, laughing. I've also tried, so all of those before are what I call the few shot settings. So you have some existing animation used as demonstration, and then you ask it to produce other animations on the same model. Those tend to work pretty well. I've also tried some zero shot settings, meaning that you don't give any existing demonstrations on this model, and you just say, okay, can you just make this happen? This is much more difficult and only works for smaller models. And like simple ones. I'll just show you some examples. So one is here, is kind of a stick man, you can walk, can cheer. The other one is like a bird model. You can ask GPT to flap the wings of the bird. The last slide I have. So it's also very easy to include kind of humans in the loop for this. So one thing is that once you have generated these animations, it's very easy to fine tune them if you're a human animator in the Unity editor. The second thing is you can also, if you are lazy, you can also like further prompt GPT to do it actually. So I'll show you one example. So on the left here, right, I prompted GPT to do bowing for the raccoon, and you see that it's actually trying to do it, but the direction is incorrect. So it's going backwards instead of forward. So then I asked GPT, okay, you've made a mistake. Can you make the raccoon bow the other way? And it does fix it. So yeah, so there you go. I think that's all I have. Thank you. Very good question. No, my summer ran out, but that's the next thing I will try. I think I would really like it's kind of some kind of transfer learning, I guess. Like very interesting, right? Like if you have a lot of demonstrations on fish, like a whale, how well can you like transfer into like some other kind of marine animals that's like somewhat similar bone structure, and how does those like affect? Yeah. 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 Maybe. Yeah.
So Eric actually had a question. He said,
Okay.
So dealing with the joint limits and forward inverse kinematic issues are learned from the training set.
I guess so. Yeah. So yeah, for sure. I mean, right, IK is very hard, right? So somehow GPT has some physical intuition as to how to do this, I guess. And I don't know if it has seen animation text like that format in its training set. But yeah, obviously it knows like it can do something about it.
Like the cheering. Like
Uh-huh.
it somehow knows that
Yeah.
language, that cheering
Uh-huh.
involves goofy arm motion.
Yeah.
right?
Yeah.
This is fantastic.
Thanks.
So my question is maybe kind of related to that. So since like Unity is so popular, presumably there's a lot of like educational content items that you can.
Uh-huh.
Right?
Uh-huh.
Do you have any sense of like how specific this kind of is to Unity, or if it could potentially be applied?
Yeah. Okay. Great question. So I cannot say for sure because we have only tried Unity. However, maybe I can't talk about this, but I will just say that people have tried it for also Babylon.js, if you know what that is. It's you can think of it as like as something that's also a game engine, so like has physics and all that. But the good thing about it is it can run on browsers. I think it's yeah, some kind of like it can be ran on browsers, so very cross-platform, and I think it also works pretty well in that. I don't think anyone has tried Unreal, so I don't know if that works. Yeah. Okay. Unreal, the main problem is the following. Because both Unity and Unreal is like compile, like Unity use C# or JavaScript, but like you need to compile into script sorry, you need to compile the script into like executable before you actually execute it, right? So we are lucky to get away with like someone wrote this runtime compiler that can actually compile scripts at runtime and then dynamically execute it. I don't think the counterpart of that exists in Unreal, which is unrelated to anything here, right? But like it's just a technical constraint. I think it's yeah.
It's C++, right? So it has to be.
Yeah, it also has to be compiled. Yeah.
Do you know if, so there are, just speaking of the compilation versus not, there are languages like processing that are like meant to real-time compositional.
Yeah.
You know of any work that's being done combining that, you know, but ChatGPT and GPT and processing?
No, but yeah, someone should try it. I say.
Let's thank Bill again. So, stop the recording so you can talk about the secret stuff.